Hello and welcome. We have seen that Euclidean algorithm is an easy to execute procedure for finding the GCD of two numbers. We have already seen that finding the GCD of two numbers using the definition of GCD itself is a time-consuming, tedious task. This is because finding the GCD using the direct definition involves finding the set of all divisors of the given two numbers, then taking the intersection of divisors to get the set of all common divisors, and then find the largest among them. Euclidean algorithm is much more easier, as we have already observed. We are going to derive an identity from the Euclidean algorithm in such a way that we will be expressing the GCD of given two numbers as a linear combination of the given two numbers. This identity is very fundamental in number theory, and we will call this identity later to be the Bezout identity. We are going to derive Bezout identity using Euclidean algorithm. We start recalling the procedure involved in the Euclidean algorithm. Let A, B be positive integers, and we make an extra assumption that A greater than B. Then, using division theorem repeatedly, we get following equations: A equal to BQ naught plus R naught, B equal to R naught Q1 plus R1, etc. Finally, maybe one more step we will write: R naught equal to R1 Q2 plus R2, proceeding like this. Of course, there are the conditions that R0 is between 0 and B, R1 is between 0 and R0, etc. And R K, write in the reverse way. This is one less, which is R K minus 1 Q K equal to R K minus 2, and the last step R K minus 1 equal to R K Q K plus 0. Suppose that these are the this is correct. Q K plus 1 0. So last non-zero remainder is equal to RK equal to GCD of AB. This is what the Euclidean algorithm said. Okay. Now, to simplify things, we are going to consider that there are only 3 steps involved in the Euclidean algorithm, and we will try to observe something interesting. So, what are the 3 steps? A equal to only 3 steps in the Euclidean algorithm involved. So A equal to PQ naught plus naught. After that, B is equal to R naught Q1 plus R1, R naught equal to R1 Q2 plus R2, and the last step, the fourth step, in fact, this is not 3, we should probably take 4 steps, and in the last step we have R1 equal to R2 Q3 plus 0. So this is the GCD because this is the last non-zero remainder. So what we are basically going to do is the following. We have R2 equal to R0 minus R1 Q2 from these equations. Right, R2 from the not last equation but the equation just before that, R2 equal to R0 minus R1 Q2. We are using this equation. Okay, now we are going to use the equations even before that. So what is now R1? R1 we can see from this step, second step, that R1 equal to B minus R0 Q1. So R2 equal to R0 minus R1 Q2, but R1 is nothing but B minus R0 Q1 to Q2. So after some simplification, bringing this R0 parts together, we will get R0 into 1 plus Q1 Q2, after that minus B Q2. Okay, now we know that R0 is nothing but A minus BQ0. So substituting that, A minus B Q0 into 1 plus Q1 Q2 minus B Q2. So if we expand this, we will get what are the terms involving A, what are the terms involving B. A into 1 plus Q1 Q2 plus B into, here we have minus Q2 minus Q2 minus Q0 into 1 plus Q1 Q2. Q0 plus 1 Q2. So the final conclusion is this. This is the GCD. GCD of A and B equal to R2, and R2 we are finally getting as A into some number plus B into some number. Therefore, we are getting GCD of AB equal to A into some number plus B into some number where X, Y are integers. That is, if D equal to GCD of AB, then there exist integers X, Y such that D can be expressed as a linear combination of A and B using this X and Y. This identity called as the we call as the Bezout identity. So what does Bezout identity say? Bezout identity says that Bezout identity is the identity expressing GCD of two numbers A and B as a linear combination of A and B itself. Euclidean algorithm, using the procedure involved in the Euclidean algorithm, we can find X and Y such that D is equal to X plus BY. We will see one quick example. Now let A equal to 6, B equal to 4. So the condition in Euclidean algorithm is satisfied because we have two positive integers and we are taking a to be greater than b. So what is the GCD of these two numbers? We will use Euclidean algorithm for finding the GCD. So 6 equal to 4 into 1 plus 2. Now 4 equal to, using this 2 into 2 plus 0. Therefore, there are only 2 steps involved, and so the basis identity appears very quickly here, because we have to take only this part. 2 equal to 2 is the GCD. 2 equal to 6 minus 4 into 1 is nothing but into 1 plus 4 into minus 1. So this is our x, our y. So we expressed d equal to ax plus by. Probably one more example we will see. Express question is this: GCD of 21 and 5 as a linear combination of 21 and 35. This question. So as per our convention, we have to take the largest number as a and the smaller one as b. So a equal to 5, b equal to 1. So we have, by division theorem, 35 is equal to 1 into 1 plus 40. Okay, next step is 21 equal to 14 into 1 plus 7. So we are yet to get 0 as the remainder. We will continue. So next step is 14 equal to, using the 7, 2 into, or the other way, 7 into 2 plus 0. So we got 0 here. So this is the GCD. So we have GCD equal to 7. Now we are going to work backwards. 7 equal to 21 minus 14 into 1. That is, now substitute for 14. 21 minus, because this b is 21 and we do not want to lose b, so keep this 21 exactly like that. So 14 we have to replace. 14 equal to 5 minus 21 into 1. Now we club these 21s and 35s. So 35 into minus 1, minus 35 is 35 into minus 1 plus 21 to 1 1 minus plus 1 equal to 35 into minus 21 into 2. And by simple calculation we can see that this is correct, because this is 21 into 2, that's 42, minus 35, that's equal to 7. This is x, this is our y. So we expressed GCD 7 as a linear combination of 35 and 21, and that's the Bezout identity. Now one possible question is, in the Bezout identity, d equal to ax plus by, is this xy unique? That means that can we find another x dash and y dash such that d is equal to ax dash plus by dash? So we will, if we recall the previous example where we expressed the GCD of 6 and 4 as 6 into 1 plus 4 into minus 1, we can see that this 2 can be obtained by taking something else also. For example, if we take 6 into 3 and 4 into minus 4. 6 into 3 plus 4 into minus 4 is minus 16, 18. So this is also possible. Therefore, the xy in Bezout's identity need not be unique. This is the conclusion we have. So we can find x and y satisfying ax plus by is equal to d, but at the same time just remember that observe that this d equal to ax plus by, x and y integers appearing in that expression is not necessarily going to be unique. We will in fact see later that in the expression d is equal to ax plus by, where d is the GCD of a and b, there are infinitely many possibilities for x and y. We will actually explain a procedure by which we can find out all such and y's, satisfying the equation d equal to ax plus by. We have already mentioned that the Bezout identity is very fundamental in number theory. Using Bezout identity, we are going to see a few interesting results. One of them is actually a very familiar result, and this is sometimes referred to as the definition of GCD. Recall that according to our definition, we call D as the GCD of A and B, provided D is a common divisor of A and B. That means D divides A and D divides B, and if there is some other common divisor C, then C is less than or equal to D. But if you call one of our previous definitions, probably we might have seen in our school days, the definition follows like this: D is said to be the GCD if D divides A and D divides B. That first part is the same. The second part is something slightly different. If C is a common divisor of A and B, then C must divide D. That's the condition in some of the definitions of GCD that appear. We are going to see that that definition and this definition are actually equivalent using Bezout's identity. As a consequence of Bezout's identity, we are going to see the following. If A, B positive integers with D equal to GCD of AB, and if C is a common divisor of A and B, then show that C divides D. That means every common divisor of A and B will divide the greatest common divisor. See that according to the definition of GCD, this statement is actually not very clear, because definition of GCD just wants that every common divisor must be less than or equal to D. But here we are asking for something much stronger. C divides D, we know that D is a positive integer, and C divides D means that C is going to be anyway less than or equal to D. But C less than or equal to D does not imply that C divides D. Here we are going to say that C is a common divisor implies that the much stronger thing is C divides D. So this is a very easily provable fact from the Bezout's identity. So what does Bezout's identity say? So the identity says that there exist xy pairs such that D equal to x plus by. Now C divides A and C divides B. Implies that C divides AX and C divides by. Now this implies that C divides AX plus by. But what is AX plus by? C divides D. So this fact we verified within a minute using the Bezout's identity. Now we have another interesting consequence of Bezout's identity. The question is the following. Let A and B be positive integers and D some positive integer with two properties. Property number 1 says that D is the common divisor of A and B, and property number 2 says that any common divisor of A and B divides D. The question is to show that D is the GCD of A and B. So we need to show that if a positive integer D satisfies these two properties, then D will become the GCD of A and B. If you recall the definition of GCD, condition 1 same in the case of the definition of GCD, that D is a common divisor of A and B. But condition 2 is slightly different. So we are going to check if this can be actually taken as the definition of GCD. So if we have to show that this is the GCD, the usual procedure is to take some other number to be the GCD and show that that number and this number are exactly the same. So suppose that D dash is the GCD of AB. So we have to show that D satisfying these two conditions is the GCD, or we have to show that D dash is actually equal to D. How to show that? D dash is nothing but D. So what is the way to show that two numbers are equal? If you have to show that two numbers are equal, one possible technique is to show that one number is less than or equal to the other and the other number is less than or equal to the first one. But if you have two positive integers, if you show that one divides the other and the second one divides the first, we know that if A divides B and B divides A, then modulus of A is going to be equal to modulus of B. But when the integers are both positive, there is no need of taking modulus, and therefore A will become equal to B. So here we have to show that D dash is equal to D, and possibly the second method, that is D dash divides D and D divides D dash, is probably going to help us. So D dash is given to be the GCD, and what is the condition? What is the relation between GCD and any other common divisor? That we have already seen, that if D dash is the GCD and if D is the common divisor, if C is the common divisor, this we have already seen. In the previous problem, we have seen this. C divides A and C divides B, then C divides GCD also. So this is a fact. This is known. If D dash equal to GCD of AB, and if C divides A and C divides B, then C divides D dash. This is not. Here we have, instead of C, we have D. D divides A and D divides B. Therefore, in the place of C we have D. So D divides D dash. Now, if you show that D dash divides D also, then we are done. But what is the property of D? What is the property of D dash? D dash equal to GCD of AB, and therefore by the GCD definition we know that D dash divides A and D dash divides B. But see, what is the property of D? If C divides A and C divides B, then C divides D. So D dash divides A, D dash divides B implies by second property that D dash divides D. So we have D divides D dash and D dash divides D. Both are positive integers. These two together imply that D dash equal to D. That is, D satisfying these two conditions will become the GCD of A and B. Therefore, the definition of GCD of A and B can be equivalently taken as D satisfying these two conditions. Instead of C less than or equal to D, you can take C dividing D. Therefore, the two definitions of GCD are equivalent. What are the definitions? Definition 1 of GCD following. Let A, B positive integers. Definition 1. E is the GCD if definition 1 says the following: E divides A, E divides B, if C divides A, C divides B, and C less than or equal to D. This is definition 1. What is definition 2? AB positive integers, D equal to AB if put 1 dash, A divides A and B divides B, and is 2 dash. If C divides A, C divides B, and C D. This is the second condition. These two definitions are equivalent. This is what we have observed. So either of these we can take as the definition of GCD of A and B.